what we'll end doing with these two distributions is we are actually going to find the differences between their means and say, is this difference really significant? And therefore, you need a comparison distribution of differences between means. And to create that comparison distribution, you take these distributions here with their own variance. And their variance, when you look at differences between variance, you actually, it's a weird thing. Instead of subtracting the variances, you add the variances. It's a counterintuitive process. You sort of accept it. I'm not going to go into explaining why. There is a mathematical reason that differences between variances is actually the sum of the variances. It has a reason. If you think about it, it will come to you intuitively. But the point is, differences between variance is really the sum of the variance. So the variance of this distribution is really the sum of this plus this. So it'll be 2. Okay? So the variance, so S, and this is going to be called S diff, because it's the distribution of differences between means. S diff is equal to S squared diff is equal to variance of S squared m1 plus S squared m2, which is equal to 0.9 plus 1.1, which is equal to 2.0. So this is your S diff, this is your comparison distribution variance. It's a weird thing. You have to accept it, and the variance is really the sum of the differences between variance is really the sum of the variances of the original of the distributions that you're summing. Okay, so so you found the variance. What's S diff? The standard deviation? Yeah, what is it? It's square root of 2. And square root of 2 is square root of 2, 1.41.
So the other one is S diff squared?
Yeah, S squared diff, yeah. Because we're summing up S squared m1 and S squared m2. So S squared diff, which is 0.9 plus 1.1, which is gives us 2. S diff is 1.4. So this is number 1 from the comparison distribution. This is number 2. What else do we need? We need the mean of the comparison distribution, pop m or whatever you want to call it. And we need the shape. Okay, so let's think about the mean now. We sort of left the mean aside for a while. Right? We left the mean. Yes, sir.
So for this distribution, you only really need the S squared to get to the comparison distribution. So for the both parts, the S and the pop mean for both sides don't really matter.
Say that again. Go
so
slow.
when you're working down the problem, starting with S1, S squared 1, S1, and S squared 2, 2, you only really need the S squared.
Yeah, you only need the variances.
You
Yeah,
only need the variance until you get to the comparison distribution.
exactly. Because
None of the other stuff matters.
yeah, none of the other stuff matters. Now, the means matter. The means matter. And we're going to now tackle the means. Okay, are we ready to tackle the means? The means matter. Look, our objective is to compare these two means and ask the question, are these two means different from each other? Is there a difference between these two means? Did the introduction of the treatment in this population or in this sample make it very different, their mean very different from this mean? And the question is, this comparison distribution, remember, this comparison distribution is distribution under what? Under the null. Well, what is the null in this case? That the means are equal. Therefore, you can say that the mean of this guy is what? 0. How do you come to that? You come to that by the following. If the mean of this distribution is something, we don't know what it is, and the mean of this distribution is something, and we don't know what it is. But under the null, if these were original populations and there were no differences between them, this question mark and this question mark have to be equal. Under the null, these means are equal. So question mark equals question mark, although we don't know what they are. Similarly, this will have a question mark too, a mean, and this will have a mean of a question mark, and they are going to be equal. So question mark 2 equals question mark 2. Now, when you actually subtract, you see you've done these here, and you subtracted the variance, right, by adding them, because I told you it's sort of counterintuitive. But if you subtract the means of these guys, and they're equal, what do you get here? 0. When you subtract equals, you get 0. That's why the distribution here is going to have a mean of 0. Everybody get that? Always. In fact, we don't even compare it to that 0. So the 0 is sort of irrelevant. But just for your information, the distribution, the comparison distribution of difference, this is not difference scores, comparison distribution of differences between means. This is a comparison distribution that has a name. And it's a comparison distribution of differences between means, because that's what we're looking for, differences between these two means, is going to have, under the null, it's going to be 0. Differences between the means under null is 0. OK, so we've described OK, and what's the shape? The shape is, what do you think? Since we've estimated, it's a T distribution, very good, T distribution with how many degrees of freedom? With the total degrees of freedom, which is what? 9, exactly. It is the sum of the 2 degrees of freedom from each. It's the total degrees of freedom, 9. T distribution with 9 degrees of freedom. Yes, sir. The what? Pop MM, yeah, here would be 0. Would be 0. Yeah, you're right. Excellent. So we found the comparison distribution. Yes?
What's the notation you're using for mean there?
Pop MM. Pop MM. Pop MM. OK, so excellent, excellent. So you know, it's complex, but it is really just a build-up on what we've done. Not really a huge jump. There are a few things that we've added to the conceptualization of this. But what you've done here is you found the 4 things that we always have talked about, and these are the things. OK, now we go to step number 3. Determine your cutoff point on the comparison distribution. This is exactly like before. What is the cutoff point? It will be, let's go back to the problem. Let's go to the problem. The problem is using the 0.05 level, does including a child name make any difference? So it's two-tailed, it's 0.5. We go to the table on page 439. Page 439, we get to two-tailed test. And we go to 0.05, and we use degrees of freedom total. Okay, because that's what we used that big number to make it easy for us to reject the null. That's a smart move. So everybody, pay attention with me for 1 second. So you know, if we had used only one side of this symmetry, if we used the degrees of freedom here or here, we couldn't have gone to degrees of freedom 9. We would have had to go to either degrees of freedom 6 or 5, which would have meant that we would have had to really have an extreme score to reject. But since we pooled everything, we now have more power to reject. Everybody with me? Do you see the importance of pooling? It gives you more power to reject a null. So we go to 9, and we go to two-tailed, and the cutoff is 2.262. 2.262 on either side. So it'll be 2.26 minus 2.262 minus 2.262 and plus 2.262. Okay, so these are your cutoff scores. Everybody with me? Step number 4, is determine determine your sample score on the comparison distribution. It will be a little bit different again. The difference here is your sample score isn't just this sample or this sample. It really is the difference between the samples. Because you asked the question, did the treatment make a difference between the two groups? Okay? So you subtract one from the other. So you can say mean 1, so t, your t now, is equal to mean 1 minus mean 2 over, now you're basically doing the same old stuff. You're asking, is the difference between these two scores significantly big enough using what yardstick? What yardstick are we using? Exactly. We're using the yardstick of the comparison distribution, which is SDiff, divided by SDiff. Is the difference really significantly different from 0 using the yardstick of this comparison distribution? And the answer is as follows. M1 is 6 minus M2 is 7.8 over SDiff is 1.41. 6 minus 7.8, 6 minus 7.8 equals minus 1.8 over 1.41, which is equal negative 1.23. Negative 1.23 is actually here. So this difference is not that significant. This doesn't reach, it's not extreme enough. We fail to reject the null. So we fail to reject the null. That's step number 5. How are we doing on time? Are we okay? Thank you. Sorry, 1.28, where are you pointing?
You're off a couple points.
Yeah, negative 1.8 divided by
Becomes a
1.8.
negative
Oh, 1.28. Yeah, sorry, 1.28. Here we go. So it's still not big enough to reach the cutoff points. It's still not, you can't reject 1.28. Okay. So, so let me just again one more time sort of put things together so that you can see how these things progress. You've got one sample and you've got another sample. This sample, you can treat it as if the way we treated the previous single sample. You use that sample to estimate a variance of the original population. And you do the same thing. You estimate the variance of the original population. However, you don't go ahead and just calculate your sampling distribution. You pool the variance. This is a new concept. The pooling is a new concept. So that's new concept number 1, pooling. You pool it by weighing the bigger sample and then summing them together. So you weigh it, degrees of freedom 1 over degrees of freedom total. You weigh it. You weigh this, and you multiply by the bigger weight, and you multiply by the smaller weight, and then you add whatever is the result. If your sample sizes are equal, you just average them. You take the two numbers and you divide by 2. Just take the average. OK, so you've pooled it. Now, when you've pooled it, you go back to what you've done before. You pool it, and then you divide by n. But you need to remember to divide by the right n. This is n1, and this is n2. At that point, you find what you've always found, which is the sampling distribution value, the sampling distribution variance. And then from there, this is the new concept. You find a comparison distribution. This comparison distribution is different from the previous comparison distribution. It's a comparison distribution made of differences between means. It's a mean of differences between means, a sampling distribution of the means with differences between means. What you want to compare to in the end is means. So you need to create a comparison distribution made out of differences between means. So this is your comparison distribution. You sum the variances of these two instead of subtract them. But then you subtract the means, and we know the means are equal, so subtracting equals get you 0. And you find so the mean is 0, which will always be 0. The shape is the t t-distribution with the total degrees of freedom, and the variance is made out of the sum of the two variances here. And then you go ahead and do what you've always done, which is you find your cutoff points, you subtract the means of the two groups, and you divide those two means by the standard deviation of the comparison distribution. How many feel comfortable with this? Some? Sorry? Yes, it's done. We were failed to reject the null. What?
See in homework if I
Right.
am comfortable with it.
Yeah, well, you have to try it. We're going to review it next time. You're going to try it. We're going to review it next time. Hopefully, by next time, you'd do very well. So I've stolen one of your breaks. So I'll let you. No, but no, just don't jump yet. Just relax. Any questions? No questions. Anybody? So who wants to rephrase just before we go? I'm going to take only 3 minutes of your time. Who wants to rephrase the concept of homogeneity of variance? Yes, Austin.
The homogeneity variance assumes that because they're both picked from the same original population, then they should be very close because since they're random, they should both represent the original sample equally as well.
Exactly. Very good. And that allows us then that homogeneity of variance assumption. No, listen, guys. So that homogeneity of variance assumption allows us then to pool. I mean, the reason we have that variance assumption, that homogeneity of variance, is that we then can pool. Because if we didn't assume that they're equal, we can't pool them. But the fact that we assume they're equal, which is a very reasonable assumption, we can pool them. And pooling gives us what? Less room for error, excellent. More power to reject the null because you have bigger degrees of freedom. You guys are great. So watch the videos. Put your remarks on the videos. See you next week. Practice. Do the homework. Thank you.